Yes, also from my part, thanks for sticking around. Okay, so as promised, the second part is going to be about polytopes. So in this case, this lecture, we're going to consider positive geometries of arbitrary dimension b, but all boundaries are going to be linear. So the components of y, they're all going to be hyperplanes. Okay, so the setup is P sits in Rd. It's a d-dimensional convex polytope. And I'm going to represent polytopes by means of their facet representation. So I'm going to describe a polytope by writing down finitely many linear inequalities. Here's some more notation. So the minimal facet representation of P is going to be this. I'm going to look at all points y in Rd. So y is short for y1, y2, yd. Satisfy u, y plus z, non-negative. U is a matrix of size n times d, and z is a vector in Rn, column vector in Rn. And the way you should read this is, well, for each row, each entry of this vector gives you an inequality. So this really means the ith row of u dot y plus the ith entry of z. It's non-negative. We'll do an example. Okay. The facets of P are going to be important. So curly f of P is the set of facets. And for one of these facets, I will write, I will index this inequality. So each of the facets of P gives me one of these inequalities. And I will use that facet for the index just to emphasize that I'm talking about this facet. Okay, so that's what I'm going to write now. So F is the intersection of P with the hyperplane given by U sub F dot Y plus Z sub F. And then curly V of P is our vertices. Okay, before I continue, let's do our running example is going to be a pentagon. So here P is a convex polygon. So this is y1, y2, and R2. The inequalities are given by, I need 5 of them, because there's 5 edges. The way you read this is the points inside this pentagon, that they satisfy this dot this. So y1 plus 1 is at least 0. This reads y2 plus 1 is at least 0, and so on. Okay, so the first one gives you this half space, second one gives you this half space, and if you intersect all of them, you get the pentagon. So the origin in this picture is here in the middle. Okay, so this is the matrix U. This is the vector Z. These two and Okay. Just one thing to note, so how do you find this matrix U? You just look at your polytope and you collect the inward pointing facet normal. So the way I set this up is you need to look at the vectors perpendicular to the facets and you need to make them face inside the polytope. Okay, so the first row of U is this, second row is this, and I went around counterclockwise. Okay. This is clear, just notation. Okay, so minimal means that I don't add an extra hyperplane. I could also say, you know, this is larger than minus 100 and this is an inequality I could add. It would change nothing about my pentagon, but it would give me 6 rows in the matrix U, and it's now this facet representation is no longer minimal. So minimal just means I only use the inequalities that I need. Okay. Bit more notation for a facet. I'm going to write H sub F. This is the hyperplane, the facet hyperplane corresponding to the facet F. To stay true to our projective setup from the previous lecture, I'm going to take the closure in the projective space of this hyperplane. Closure of this in the d-dimensional projective space. So that means for this facet right here, this line segment right here, the blue line, so H sub F is a blue line in P2. As a point at infinity. Okay, and then our algebraic boundary will be Y, like in the previous lecture. So the algebraic boundary of the polytope P is the union of all these facet hyperplanes. Okay, so to reiterate, what I need to do is I need to take the Euclidean boundary, which is a union of 5 line segments, and then take the Zariski closure. So the smallest algebraic curve containing this union of line segments is the union of 5 blue lines in P2. Okay. All right. For a vertex V, I'm going to write U sub V, the submatrix of U, given by, just going to look at all the rows of U that correspond to facets which contain V. So this vertex V is contained in the facets 1 and 2. This is the first row of U, second row of U. So the submatrix of U is this 2 by 2 submatrix, U sub V. Okay. A couple things I need to tell you what the canonical form of polytope will be. So I'll tell you that that polytopes are positive geometries in the sense of, well, in fact, both definitions that I gave. But I will sketch the proof in the case where the polytope is simple. Okay, so that's an assumption I impose. P is simple. Means that UV is a square matrix. Okay, strange way of saying it. For each vertex. So a polytope is simple if each vertex is contained in dimension many facets. Okay, you can imagine every polygon in the plane is simple because a vertex of a polygon is contained in two edges. But in 3 dimensions already, you can imagine a pyramid with a quadrilateral base. And now the top of the pyramid is contained in 4 facets. That's not allowed. In a sense, this is a non-generic situation because if you you wiggle the facets a little bit, you break it. Okay. So the reason I want to make this assumption is because I really like the formula for the canonical form of a simple polytope. Here's the so P sits in RD, sits in the real points of the d-dimensional projective space. P is convex and d-dimensional as always, but in addition, it's simple. And this tuple d-dimensional projective space comma P is a positive geometry. And so by lamb. Its canonical form is as follows. So there's different ways to write this. This is my current favorite. So you take a sum over the vertices of P. In each term, there's a numerator that is just the determinant of this square submatrix, the determinant of the yellow matrix, and you take the absolute value of that. The denominator, you take a product of some of these facet equations. So remember, our canonical form needs to have poles along the boundaries and only along the boundaries. So here I'm going to take a product over all faces containing my vertex. You just write down. This is the form. Moreover, if you take the relative homology class of P, the genus 0 pair projective space comma YP, and this is a positive geometry. Sense of what I called the BB definition. And if you send this relative homology class through the omega map from the Brown-Dupont paper, then that's the same as this thing. But not only do the definitions agree that they're positive geometries, they also agree on the canonical form. Okay, I want to sketch the proof. So the proof is by induction on the dimension. And, the base case is D is 1. So if D is 1, then there exists essentially only one one-dimensional polytope, and it's the line segment AB. And its U matrix is 1 minus 1, and its Z vector is minus A, B. Okay. So the line segment has 2 vertices. So this formula will have 2 terms. you can check this. So this is just b minus y is just what you read from the second row, and y minus a is what you read from the first row. Okay, and the coefficients are 1 because the u is unimodular. Okay, and then this you can expand it. This is exactly the canonical form of the line segment AB that we wrote down 2 hours ago. Convinced for D is 1? Okay, good.